we are going to start our discussion of the review notes over covalent bonding with a little review of ionic bonding. Okay, we did the gizmo yesterday. We did review notes of ionic bonding yesterday. And we should know that electrons are being transferred. Okay? Electrons are being transferred. This is an interaction between a metal and a nonmetal. The resulting substance we refer to as a salt. So, if you remember on the part we just answered of the gizmo, where you put all of the different substances together, and I am talking about lithium and fluorine, beryllium and oxygen, magnesium and fluorine, okay? Any one of those could be referred to as a salt. So when we have a metal combining with a non-metal to form ionic bonding, where we have the transfer of electrons, we refer to that as a salt. So if you look at here, one of the most common ones, we showed this to you yesterday. Sodium has one valence electron on the 3s level. Chlorine is also on the third energy level, but chlorine has 7 valence electrons. Well, what's going to happen? Sodium is going to become a positive ion that we call a cation, okay? Because it gives up an electron. If it loses an electron, instead of having 11 electrons, sodium only has 10. However, sodium still has 11 protons, net charge of 1. Chlorine has gained an electron. So instead of having 17 electrons, chlorine now has 18 electrons. Still has 17 protons, so the net charge is a -1. A negative ion is something that we call an anion. So the cation and the anion have the electrical attraction. Therefore, this is an anionic bond. Now, when we talk about molecular compounds, okay, we are talking about sharing electrons. Sharing electrons. These occur between nonmetals. As you can see, I have 2 fluorines right here. Fluorine is a nonmetal. Fluorine has 7 valence electrons. Fluorine is a halogen. Fluorine needs 1 more valence electron in order to complete its outermost energy level. Therefore, if you look at this fluorine, the red one, all the red dots are the red fluorines. All the black dots are the black fluorines. And if we think of this kind of like a Punnett square, where in this circle is this fluorine, in this circle is this fluorine, but in the middle, what happens? That's for both fluorines. So, what is actually happening with these 2 electrons is they are sharing the electrons. So if you look strictly at the red circle, does it have 8 electrons around it? Does the red fluorine in the red circle have 8 electrons around it? Yes, so that satisfies the octet rule. Does the fluorine in the black circle have 8 electrons around it? Yes, so that obeys the octet rule. So these two electrons are being shared by both fluorine. That is the sharing of electrons. That is a covalent bond. Now let's compare salts versus molecules. Ionic bonding versus covalent bonding. Okay. A metal cation, a nonmetal anion are salts. We just said covalent bonds are nonmetals, and we refer to them as molecules. Okay. If we look, on the left is a covalent bond. These two are sharing the electrons. On the right is an ionic bond. This atom, whatever it is, has transferred an electron. I wonder why I've got that on there twice. Di. What is di? What is di? Two. Diatomic molecules. Break those down. They are molecules of two atoms. We will talk about these in greater detail later on, but we're going to start now discussing the Super 7. You probably don't have these in your notes yet, so you might want to just say, the Super 7. The Super 7 are the 7 diatomic molecules. They are molecules, so they are covalently bonded. They are sharing electrons. Now, the thing about the Super 7, the way I teach you to remember the Super 7 is look at this. Even if you can't read this, doesn't that make a 7? Isn't that a 7 right there? Okay. Now, if you look on my periodic table up here, where I have element number 7 is nitrogen. Okay. So there are 7 diatomic molecules. They start with nitrogen, which is number 7, and on the periodic table, they make a 7, other than hydrogen. So if I look on my periodic table up here and say, okay, what 7 are my diatomic molecules? I say, okay, let me start with 7. Here they are. Nitrogen's 1, oxygen's 2, fluorine's 3, chlorine's 4, bromine's 5, iodine's 6, and then my 7th one over there is hydrogen. So, there are 7 of them. They start with nitrogen, which is element number 7, and on the periodic table they make a 7. That's why we call them the Super 7. Molecular compounds are either liquids or gases at room temperature. Here we have some examples. They're either liquids or gases at room temperature.
Teacher, explain the selection of the following students are in the building. If you have them in class, please notify the office immediately. Bailey Garrett, Hunter Haynes, Haley Kirk, Hunter Markins, Tim Piper, or Gage Amy. Those students are in the building. Please notify the office. You come down the office at this time. Thank you.
Molecular compounds have lower melting points than ionic compounds. This means that they are weaker than ionically bonded compounds. Okay? We'll do a gizmo coming up, I believe, later on the week. We'll do a gizmo that'll show us these lower melting points that the molecular compounds have compared to the ionic compounds. If I look at my chart here, okay, just some important facts, okay? Ionically bonded substances are called salts. Covalently are called molecules. Ionically transfers electrons. Covalent bonding shares. A metal and a non-metal for ionic, non-metals for covalent. Ionic compounds are solids. They have melting points above 300 degrees Celsius. They dissolve in water, and they are very, very good conductors of electricity. However, properties of covalent, most of them we just said are liquids or gases at room temperature. Their melting point is below 300 degrees Celsius. Not really a good classification for their solubility, but their conductivity. They do not conduct electricity very good at all. Now, we know that ionically bonded substances transfer electrons in order to obtain that noble gas configuration that gives them stability. Covalent bonds will achieve that same stability by sharing electrons. So once again, we're still trying to fill the outermost energy level. We're still obeying the octet rule, which states that we need 8 valence electrons in the s and p orbitals. So we're still trying to achieve that same thing. However, we're doing it by sharing electrons instead of transferring them. Now let's look at a single covalent bond. A single covalent bond consists of 2 electrons being shared by a pair of atoms. So we have 2 electrons that are shared. Here is hydrogen. We stated that hydrogen was a diatomic, a super 7. So hydrogen will bond with itself to form a diatomic molecule. Remember, hydrogen is an exception to the octet rule. Why? Why did we say hydrogen's an exception to the octet rule? It only needs 2 electrons to fill its valence level. So by sharing these 2 electrons, hydrogen has filled its outermost energy level. So when we signify this, we put this hash in between the 2 hydrogens. And that hash is telling me that I have shared 2 electrons between those 2 hydrogens and that I have a single covalent bond. Here are some more bonds. All right? As I'm looking, and I like to at times color code these folks, but here's electron dot notation. Here's a Lewis dot structure. We'll do this later also. Here's a Lewis dot structure where chlorine has 8 electrons around it. Hydrogen has 2. Remember, hydrogen only needs 2. So hydrogen is stable. Chlorine is stable because of these 2 electrons that are being shared. Now, just some terminology that I would say we've probably been through. We'll go through again. This is what we call a shared pair of electrons because it's shared between the hydrogen and chlorine. These electrons are only the chlorines. So those are what we call unshared pair of electrons. Here we have an unshared pair with nitrogen, and nitrogen is bonded to 3 hydrogens. So here's a single covalent bond, here's a single covalent bond, here's a single covalent bond. As we're looking at these, I see 4 dashes right there. That tells me that the carbon has formed 4 single covalent bonds. Here is water. Here's a bond, here's a bond. So water has 2 single covalent bonds. I just told you about shared pair of electrons and unshared pair. What are the shared pair of electrons here, folks? Who can tell me where the shared pair of electrons are? What are they signified by? Yes, Cindy? The dashes. So these 4 dashes are shared pair. What are the unshared pair? What are the unshared pair electrons? Fletch? Okay, what color are these? Green. All these green electrons are unshared pair. Those are strictly the chlorines. Okay? Now, double covalent bonds. Double covalent bonds are the sharing, okay, this says 2 or 3, 3 or triple, the sharing of 2 pair of electrons, 4 total electrons. So if we have a double bond, we're sharing 4 electrons, 2 pair. If I look at this oxygen right here, okay, I signify 2 dashes, meaning a double bond. Those 2 dashes are 4 total electrons. So if you see these 4 blue spheres here, are electrons being shared by both oxygens. So if I look, the oxygen on the right has 1, 2, 3, 4 of its own electrons on the outermost energy level, and then it is sharing 4. Same thing with the oxygen on the left. 1, 2, 3, 4 electrons, and then sharing the 4. So they are both obeying the octet rule. Here's another one. Okay, here's another one. Carbon, double bond, twice with oxygen. Okay, carbon's double bonded twice with oxygen. So this double bond represents how many electrons? How many electrons does that double bond represent? 4. How many does that represent? 4. So if you look at this, carbon's got 4 here, it's sharing. 4 here, it's sharing. Would that obey the octet rule? 4 and 4? Yeah. A triple covalent bond is the sharing of 3 pair of electrons, or a total of 6 electrons. 3 pair, 6 total electrons. Nitrogen is the most common example of this. Okay? We know nitrogen, looking at your periodic table, how many valence electrons does nitrogen have? How many valence electrons does nitrogen have? What do you think, Alexa? 5. 5 valence electrons. So if you look at this nitrogen, here's 1, here's 2, 3, 4, 5. You look at this nitrogen, 1, 2, 3, 4, 5. They still have 5 valence electrons, but nitrogen needs 3 more to hit the 8, right? So these 3 are going to be shared between the 2 nitrogens. Now, when I draw these out, people, when I draw these out, I like to use color. So I'm going to put this nitrogen here, And I'm going to show you that it has these 3 dots. And I'll just put these over here. They're there for a reason. This nitrogen also has 5 valence electrons. So as I'm looking at my little color coding here, the red nitrogen has 5 valence electrons of its own, correct? If it takes these 5 and shares 1, 2, 3, that makes 8. If the blue nitrogen has its 5 and shares these 3 red ones, that makes 8. So once again, we're still obeying the octet rule. We're just arranging our electrons in different ways so that they would be sharing. They would be sharing them. Okay? I even like the little Punnett square bit thing to show that, hey, here's this nitrogen. Does it have 8? Does that nitrogen have 8 electrons? Yes, it obeys the octet rule. Does this nitrogen have 8 electrons? Yes, it obeys the octet rule. Okay? And that these 6 are the 6 electrons that are being shared in the covalent bond. Okay? Now I believe, if I remember right, my next slide right here should, or my next part this, should have the 3 dashes that represent a triple bond. So 3 dashes there represent 3 shared pair of electrons for a total of 6 electrons. Now finally, here is what we are looking at when we talk about single, double, and triple bonds. Okay, here's the bottom line. Here's the dash method of a double bond, the dash method of a triple bond. Here are the 3 shared pair of electrons. Count them up total. Each nitrogen has 8. Here are the 2 pair of electrons being shared, or 4 total. And here's the 1 pair, the single pair, 2 total electrons of a single covalent bond.